So now let we start again. In the last class, we have discussed about the concept of unit root in terms of the value of the characteristic roots relating to the AR characteristic equation. If the characteristic roots is equal to 1, then the autoregressive process will contain unit root. Now, how many unit roots a series may contain depend on the order of autoregression, because the autoregressive characteristic equation depends on the order of the autoregressive process. For example, in AR1, the characteristic equation is a linear and the number of characteristic roots is equal to 1. Therefore, in AR1, the possibility for unit root is equal to 1. On the other hand, for AR2, you have a quadratic characteristic equation. So for a quadratic equation, you have two roots. Now, if the value of both the roots equal to 1, then the series will contain 2 unit roots. If one of the root is equal to 1, another one is less than 1, in that case, the series will contain 1 unit root. If both the roots less than 1, in that case, the series will contain no unit root. So the number of unit roots present in a series depends on the order of autoregression. We are more concerned about the autoregressive part of the series as compared to the moving average. Simply because we have discussed earlier, the moving average part by definition is always stationary. So the non-stationarity problem particularly will be related to the part of autoregressive. For that reason, we are more concerned about the autoregressive process than the moving average process. So we are discussing the characteristic equation relating to the autoregressive part, not relating to the moving average part. As we have got the characteristic equation for autoregressive part, similarly we can get the characteristic equation for the moving average part, and by solving we can get the characteristic roots for the moving average part. And in that case also, if the values of the roots equal to 1, the moving average component will contain unit root. But the presence of unit root in moving average component is less problematic as compared to the presence of unit root in the autoregressive component. Okay, so for that reason, we are more concerned about the autoregressive part as compared to the moving average part. Now, in autoregressive part, if the value of the roots equal to 1, then the series will be non-stationary with unit root, or in other words, the series will contain the stochastic trend. We have discussed all these things in our last class. Now today, our main task is how to locate the presence of unit root in a series. In other words, how to identify whether a series we have is non-stationary with stochastic trend. Because in reality, we have only the data series. Data series for X, data series for Y, data series for Z, etc. So in reality, we have a data only. We don't have, and on the basis of the data, we can calculate the characteristic equation, we can calculate the characteristic roots, or we can calculate the value of the roots to finding out whether the value is equal to 1 or less than 1 or greater than 1 in reality. Conceptually, we have defined unit root in terms of the values of the roots. Okay, but when we have a data only, on the basis of the data, how do we identify whether the series has unit roots? So this is the topic of discussion for today. So unit root means, as I have already mentioned, the characteristic roots equal to 1. Okay. And the presence of unit root implies the series is non-stationary, exhibiting stochastic trend. The question is how to check it. The initial part of checking whether a series contains unit root or not is just to plot the data. So we have the data, we can plot it. By plotting the data, we may have some idea about the nature of stationarity, nature of non-stationarity, nature of trend, etc. For example, let we consider two hypothetical data series. We have shown in this handout. In this figure, we are considering two cases, case 1, case 2. And obviously the behavior of these two cases are not similar in all respect. First of all, the both series experiencing fluctuations a lot. But the nature of fluctuations in series 1 and the nature of fluctuations in series 2 are not similar. Okay. In the right hand side figure, we have fluctuations with some trending behavior. Fluctuations are showing downward trend, then upward trend, etc. But in the figure shown in left hand side, there is no systematic trend in the fluctuations. So although both the series shows a lot of fluctuations, there may be a trend in fluctuations in the series shown in the right hand side. For that reason, we may have some idea that if a behavior of a series looks like this, it may contain unit root. Or if the behavior looks like this, the series may not contain unit root. I am using the term may or may not because this is the simple gauging just by looking at the time path. We are not sure whether in this case the unit root presents or not, but we have some rough idea just by looking at the figures. And if we compare both these figures, there is some common feature. The common feature is there is no clear-cut trend either in this or in this. Again, if we look at another two series, the basic difference between these two series and the series we have shown earlier, in our earlier series there was no trend. No trend means the trend we can observe. But in this case, we have a trend. The value of YT shows upward movement in this case. The value of YT shows upward movement in this case. So in both cases, the value of Y or the value of the variable moves up over time. Therefore, the values of the variable exhibits some kind of trend, which is visible. But in our earlier case, the trend was not visible. Okay. But although the trend was not visible in this case, there is a possibility of unit root in the figure shown in the right hand side. Because of the nature of fluctuations could be measured in terms of the variance of the variable. And we have defined if the variance shows some kind of trend, then the series may contain unit root. Okay, so in this case, there is a possibility of trending behavior in the variance, not in the mean value. But the figures shown here, there is a possibility for trend behavior in mean value as well as in the variance. But if we look at closely, the behavior shows in the left hand side and the behavior shows in the right hand side. In the right hand side, the fluctuations is more irregular as compared to the left hand side. Therefore, we may have some idea that the variance involved in this series may have some kind of trend. But the variance involved in this series may not have some kind of trend, because the variance looks like roughly uniform here. But here the variance is not uniform. Therefore, there is a possibility of unitude in the case shown in the right hand side, but there is no possibility of unitude in the case shown in the left hand side. So all are the possibilities. So after having some idea but looking at the series, next we can go through the formal testing by using some statistical norms. Now, if you are interested, I can show you some real data. These are the hypothetical figures based on the simulated series. Now I have some figures from, have you seen this? Is it visible to you, the data file? Have you seen the data file?
No, sir.
No, sir.
Sharing.
No, sir.
Just
No, sir.
for you. Okay, so it will take some time. So let we again come to the our earlier discussion. So if the behavior looks like this, there is a lesser possibility of presence of unitude. If the behavior looks like this, the possibility of presence of unitude is high. So after having some idea, just by looking at the behavior of the series, then we can proceed for the formal testing for unitude. Now, a lot of statistical tests are available in the literature. We can discuss here a few, and we start with the basic test for unitude, what is known as the Dickey-Fuller unitude test. Dickey and Fuller, two statisticians, formulated this test in 1979. And this test in time series econometrics is popularly known as the Dickey-Fuller test. This Dickey-Fuller test considers only the AR1 series, autoregressive of order 1. Now, let us start with AR1 series. So, we may have different form of AR1. Just look at the possibilities shown in equation 1, 2, and 3. In equation 1, YT follows AR1. In equation 2, YT follows AR1. In equation 3, YT follows AR1. But the basic difference is, in equation 1, there is no intercept term. In equation 2, there is an intercept term. In equation 3, there is an intercept term along with the deterministic trend. But in all cases, YT follows AR1 because YT depends on its past values only, one period back value. YT is equal to phi 1 YT minus 1 plus epsilon t. In the second equation also, YT is equal to phi 1 YT minus 1 along with the intercept term. In the third equation, YT is equal to phi 1 YT minus 1 along with the intercept term. So we can consider these three types of AR1 series. First type is called AR1 without drift parameter. second one is AR1 with drift parameter, and equation 3 is AR1 with drift as well as with the deterministic trend component. Okay, so in all cases, testing for unit root relates to the value of the coefficient phi1. And we have discussed in the last class, for AR1, incidentally, if phi1 is equal to 1, there is a unit root in the series. Because in AR1, the value of the characteristic root z is equal to phi1, we have shown. And if the value of z is equal to 1, then there is a unit root. And in the case of AR1, if the value of phi1 is equal to 1, then we have unit root in AR1. Because in AR1, phi1 itself is the value of the unit root. Value of the characteristic root, sorry. So if the value of phi1 is equal to 1, then the AR1 series contains unit root. So we have to test here. So the testing for unit root relates to the coefficient phi1. But the nature of testing depends on the actual specification of the AR1 series. AR1 may look like this or this or this. So how to decide whether our data follows this type of AR1 or this type of AR1 or this type of AR1. So for that purpose also, we have to plot the data. After plotting the data, we have to decide which kind of AR1 would be appropriate for our case. Okay. In this case, there is no intercept. So if your series passes through the origin, then you can consider AR1 as shown in equation 1. In equation 2, we are allowing for the positive intercept or negative intercept. So if there is a non-zero intercept component, then we can specify the model in terms of equation 2. After plotting, if we look at the series follows some kind of trend, either upward rising trend or downward falling trend in the main value, then the more appropriate form of specification will be equation 3. So by looking at the time path of the data, we have to decide what kind of AR1 we have to consider, either equation 1 or equation 2 or equation 3. Okay, so on the basis of the nature of the time path, we have to select any of these 3 in case of AR1. So after selecting the appropriate specification, we have to estimate the model, because you know from the basic statistics, testing of hypothesis appears only after estimation. Without estimation, we cannot carry out testing of hypothesis. So the testing for unit root also needs the estimation of the model. So suppose we are specifying AR1 as shown in equation 1. So on the basis of this specification, we have to estimate the model with data. After estimation, we have the value for phi1, estimated value for phi1. Or if we specify equation 2, we can find out the estimated value for phi1 in this case also. In equation 3, we can find out the estimated value for phi1. So before carrying out unit root test, we have to estimate the model. So which model we have to estimate depends on the basic behavior of the series. And we can identify roughly the basic behavior of the series just by looking at the time path of the model. Okay. Now, conceptually, if the value of phi1 is equal to 1, then we can say that the series contains unit root. Therefore, for AR1, the presence of unit root means the absolute value for phi1 should be equal to 1. Therefore, in unit root test, the basic hypothesis we have to test is mod phi 1 is equal to 1. This is our null hypothesis. And the alternative, mod phi 1 less than 1. So in this case, the null hypothesis suggests the presence of unit root, or if you put phi 1 is equal to 1 in the AR1 specifications we have, either in equation 1 or 2 or 3, if we substitute phi 1 is equal to 1, then you have a model what is known as the random walk model. So presence of unit root in AR1 is synonymous to random walk. Therefore, the null hypothesis we have set here represents the presence of unit root in the series or the random walk. And the alternative hypothesis, phi 1 less than 1, indicates the series is stationary. So in unit root test, we have to consider phi 1 is equal to 1 as a null hypothesis and phi 1 less than 1 as the alternative hypothesis in absolute terms. Okay, and these type of hypothesis would be appropriate if we have AR1 in the form of either equation 1 or equation 2. So in equation 1 or equation 2, the null hypothesis is phi 1 is equal to 1. Alternative is phi 1 less than 1. In other words, for equation 1 and 2, the null hypothesis is presence of unit root, or the model is random walk. Alternative is the model is stationary. But if we have to select equation 3 as a possible form of AR1 on the basis of the basic behavior of the data as shown by plotting. So in the case of 3, this AR1, we have incorporated additional term, the deterministic trend. So in presence of deterministic trend, the series YT will never be stationary. In 1 or 2, YT may be stationary, but in YT, the series will not be stationary at all. So in 3, stationarity will not appear in the alternative hypothesis. So what would be the hypothesis for equation 3? For equation 3, the null hypothesis should be phi 1 is equal to 1 and beta equal to 0. Simultaneously, we have to consider these two parameters, phi 1 equal to 1, beta equal to 0. And in the alternative, we have phi 1 less than 1 and beta not equal to 0. So if you select AR1 with deterministic trend as shown in equation 1, we have to set the testing of hypothesis in this way. And we have to consider two parameters, phi 1 and beta, both in the null as well as in the alternative hypothesis. So what would be the interpretation of the null hypothesis here? If we have phi 1 is equal to 1 and beta is equal to 0, look at equation 3. If beta equal to 0, there is no deterministic trend. And if phi 1 is equal to 1, there is a stochastic trend. And in this case, the process will be called different stationary process. So if phi 1 is equal to 1 and beta equal to 0, then we have a model of random walk with drift parameter. And in that case, the YT will be non-stationary with unit root, and it could be stationary after taking some difference. That's why this kind of model is called different stationary process. So if phi 1 is equal to 1 and beta equal to 0, then the model we have DSP. So in equation 3, the non-rejection of H naught implies your series should be DSP. On the other hand, in alternative, if phi 1 less than 1 and beta not equal to 0, phi 1 less than 1 means no unit root. phi 1 equal to 1 means unit root. So there are two parameters in this test, one relating to unit root, another one is relating to the deterministic trend. So in null hypothesis, we have considered presence of unit root and no deterministic trend. In the alternative hypothesis, we have considered no unit root, but with deterministic trend. So if H0 is not rejected, it indicates the series YT will follow DSP. But if H0 is rejected, that means if H1 is accepted, then your series will be TSP, trend stationary process. So just try to compare the testing of hypothesis in case of equation 3 and testing of hypothesis in case of equation 1 or 2. So this is relating to 1 or 2. So in equation 1 or 2, our main concern is to test whether the series non-stationary with unit root or stationary. Null hypothesis indicates non-stationary with unit root, alternative indicates stationary. But in the case of 3, the null hypothesis indicates presence of unit root with no deterministic trend. Alternative hypothesis states absence of unit root with deterministic trend. So in both cases, the series is non-stationary. So there is no question of stationarity here. In alternative also, the series is non-stationary. Okay. So in the case of third possibility, we have to test unit root in absence of deterministic trend against the alternative, no unit root in presence of deterministic trend. That's why H0 implies DSP, H1 implies TSP. Clear? So I have already discussed this point, how to select the form of AR1. We have mentioned here 3 possibilities of AR1, equation 1, equation 2, equation 3. We have to select the appropriate one just by plotting the data. After plotting the data, you have to have some idea about the nature of the trend, about the nature of the series, particularly relating to the intercept turn as well as the trend component. So if the series passes through the origin, we have to select 1. If the series do not pass through the origin and do not have clear-cut trend, then we have to select 2. If the series do not passes through the origin and shows clear trend, in that case we have to select 3. Okay, so after selecting, we have to set the appropriate hypothesis. If 1 or 2 is your appropriate case, then your hypothesis will be this type: H0 presence of unit root, H1 absence of unit root. That is, H0 indicates non-stationarity with unit root, H1 indicates stationarity. But if possibility 3 is appropriate one, in that case, your hypothesis will be like this. In other words, in this case, the null hypothesis indicates the presence of unit root with no deterministic trend, and the alternative is the absence of unit root with deterministic trend. So in the third case, we cannot consider the possibility of stationarity. So always the series showing the behavior like equation 3 is non-stationary. So the question is, in this case, which type of non-stationarity? Non-stationarity with unit root or non-stationarity without unit root? So in the case of equation 3, we are testing non-stationarity with unit root as a null and non-stationarity without unit root as the alternative. Is it clear up to this point? Now the basic question before testing of hypothesis, we have to estimate the model. So how to estimate? Our basic method for estimation is OLS. So we can apply OLS in estimating equation 1 or 2 or 3. Just keep in mind the basic format of 1, 2 and 3. The autoregressive of order 1, the basic form of 1, 2, 3 just look like this. So you have to keep in mind the structure of this, this and this. So you have to estimate either 1 or 2 or 3. But if you estimate directly equation 1, there is a problem. Or if you try to estimate equation 2 or equation 3 in this form, there is a problem. What is the problem? Because under null hypothesis, you assume that the value of phi 1 is equal to 1. In other words, under the null hypothesis, in all cases, you assume that the series is non-stationary with unit root. So in the case of non-stationary with unit root, we have mentioned earlier, the series has a power of memory. The series can memorize the past. So there is a problem of serial correlation will appear under the null hypothesis in all cases. So to resolve this problem, Dickey and Fuller considers the alternative form of the equation in this way. Just look at equation 4, equation 5, equation 6. Equation 4 is relating to equation 1 we have shown earlier. Equation 5 is relating to equation 2 we have shown in earlier. Equation 6 is relating to equation 3 we have shown in earlier. So how to get equation 4? The left hand side is delta yt. In our earlier equation 1, the left hand side was yt. So how to get delta yt? Delta yt means simply yt minus 1. So if you subtract yt minus 1 from both sides in equation 1, just subtract yt minus 1 from both sides. So in the left hand side, you have yt minus 1, that is delta yt. And in the right hand side, you have phi 1 yt minus, you already have minus yt minus 1. So after taking a common, you have phi 1 minus 1 within bracket into yt minus 1. So phi 1 minus 1 is equivalent to rho in equation 4. So rho we have introduced here, rho is equal to phi 1 minus 1. Similarly in equation 5, so to get equation 5, you have to subtract yt minus 1 from the both sides, and you have delta yt in the left hand side, and in the right hand side, the coefficient for yt minus 1 becomes rho. Rho is equal to phi 1 minus 1. You have to keep in mind. So if rho is equal to phi 1 minus 1, so the hypothesis we have set earlier will transfer into this form. So earlier we have said phi naught, h naught, phi 1 is equal to 0. Phi 1 is equal to 0 now becomes rho is equal, sorry, phi 1 is equal to 1 in our earlier case. Phi 1 is equal to 1 was the null hypothesis. Now it becomes rho equal to 0. Why? This is because rho is equal to, you can write down, rho is equal to phi 1 minus 1. So phi 1 is equal to 1 will be equivalent to rho equal to 0. So rho equal to 0 indicates phi 1 is equal to 1. That is the presence of unit root. And alternative was, in our earlier case, phi 1 less than 1. So phi 1 less than 1 would be similar to rho less than 0. So we can set our hypothesis in this way: rho equal to 0 as a null, rho less than 0 as an alternative. So rho equal to 0 as a null indicates the same, that is the presence of unit root. Rho less than 0 as alternative indicates the series is stationary. Similarly, for the third specification, that is equation 6, now the hypothesis will change in this way: rho equal to 0, beta equal to 0. It indicates the presence of unit root without deterministic trend. And the alternative, rho less than 0, beta not equal to 0. That is without unit root but presence of deterministic trend. That is the first case, non-stationarity with unit root. the second case, non-stationary without unit root. So this is the basic hypothesis used in the Dickey-Fuller test. Okay, now the session will stop within less than 1 minute, so we can join again for the next part, how to find out the test statistics in the Dickey-Fuller and what is the basic features for the Dickey-Fuller test. So prepare yourself for the next joining, because we have a very few seconds, so we do not want to start. So we will start afresh from here in the next meeting just now. Okay. So I am ending this session. For the next session, we will start within a minute.